largest and most powerful space observatory. And who better to help us untangle this tonight than America's top astrophysicist, maybe the world's top astrophysicist, Neil Degrasse Tyson, joining us right here in person. Neil, thanks so much for being on Top Story.
Let's do this.
I know this is your world, and I want you to walk us through this.
It's our world.
It's our world. Okay, so let's start with this one right here. Talk to me about what we're looking at.
Your image is changing every 5 seconds here.
So I'm going to ask our great director, Brett, just to kind of freeze on one, and I think we'll start with one of them here.
Okay,
what are we looking at here?
This is the remnants of a star that has died. The sun will have a fate such as this, where at the end its outer layers of gas will escape into space and slowly drift away. It makes for spectacular, beautiful imagery of when this happens. And
when
these are called planetary nebulae.
What did you think?
Oh, I'm thinking, oh my gosh, we are seeing things better in more detail than ever before. Not only nearby, but far away.
So the red is gas, and the middle.
Yeah, all this is gas.
Okay.
This is a star that has released this gas into space, but it's called a planetary nebula. It has nothing to do with planets. It's a historical error, actually. But these objects are all over the galaxy, and this is an example of what the telescope can do. All of the structures that you can see all throughout.
Let's see another one of these beautiful images that we've seen from this telescope, and you can walk us through it. This was the original. This is the original. So this was your favorite because it got a little bit of criticism. Some people were like, "This is it. This was the first one." It wasn't me, but some people.
So bring it on.
So tell me what we're looking at here.
Okay, so first, we are looking past several stars sitting on our nose in our own Milky Way galaxy. These are the spiked objects that are here. Ignore them.
Okay.
They're just in the way.
Okay.
All right. What we're actually looking towards is a galaxy cluster halfway to the edge of the universe.
Okay.
And it has a very strong gravitational field surrounding it. Meanwhile, galaxies behind it, these that are curved into arc shapes, they're light passing through the universe, minding its own business. It sees this distortion in the fabric of space and time, and it curves in response to it. Einstein predicted this.
There could be planets. There could be another
sun, these are entire galaxies of commensurate rank and privilege, such as what the Milky Way is.
And we can't even count them.
And this is and you know how big this is on the sky? If you take a grain of sand and hold it at arm's length, the patch of sky covered by the grain of sand is what you see here. So this is just stupefyingly detailed.
I want to keep feeding this. Give me another image here. We can't stop this. Come on. What else do we have here next up? Let's see what we're seeing here. This is a beautiful one. This is the Carina Nebula.
Once again, the stars that are nearby. Oh, by the way, these spikes occur because it's called diffraction spike. Light, as it passes through the spider mounting of the secondary mirror, diffracts around it. So there's nothing cosmic about that. It's a hardware artifact within the telescope.
And then this is
an actual gas cloud, and because the telescope is tuned for infrared has good penetration depth into gas clouds. By the way, it's the same reason why your fog lights on your car are more red and amber than blue. The more red you are into the spectrum, the deeper into clouds you can penetrate. And when you do that, you have access to places where stars are being born, as well as planetary systems around them.
Are these colors enhanced at all by NASA, or is this what the telescope is seeing?
Okay, you want to go there? We'll go there. Let's do this. Yeah. Okay, so in your eye, you have red, green, and blue RGB sensors in your retina. And what happens is, what we define as visible light is the light that comes through and is detected by these three. Those get combined into a single color image of what you see in your brain.
Okay.
Now, think about that. This entire telescope is tuned for the infrared. You can't see infrared.
Okay.
But what the telescope does is it can take images in 3 different bands, separate bands of the infrared. Then you hand it an RGB and create a color picture, which is the color you would see if your eyes could see infrared. So it's authentic and legit.
We thank you so much for joining Top Story tonight. This last one, we got 10 seconds.
Okay, this is Stefan's quintet. 5 galaxies go bump in the night. I don't know if you knew that.
I thought there was no sound in space.
Thanks for watching our YouTube channel. Follow today's top stories and breaking news by downloading the NBC News app.
An airplane goes through the air faster than the speed of sound. You get a what?
You get a boom.
A sonic boom.
Sonic boom.
Okay, so now, what happens if a particle travels through a medium faster than the speed of light?
the entire universe implodes on itself.
So here's the thing.
And we all get sucked into oblivion.
This is Star Talk, Cosmic Queries edition. I got Chuck Nice with me. Can't do that without Chuck. Chuck, how you doing, man?
Well, that's not true.
Oh, actually, it's not true. That's right.
You have done this without Chuck. That's for sure.
I've had guest co-host for Chuck because Chuck sometimes is a busy man and you don't have time for us. That's how that works.
Okay, well, that's not true either.
So, Chuck, a little while ago, we did an entire Cosmic Queries on cosmic collisions, which is a very rich tapestry of phenomena and objects in the universe that go
celestial banging
in the night. And in fact, of the portfolio of public talks that I give, that is the title of one of them, Cosmic Collisions. So if a city invites me to their theater to give a public talk, and they get the list of things I can talk about, Cosmic Collisions is frequently selected in that list. So Chuck, you've solicited questions from our Patreon members, and so and I guess it's all about collisions. So bring it on.
Okay, let's jump right into this. This is Christopher Bax, and Christopher says, "Dr. Tyson and darling Chuck." Well, Christopher.
Thank you, Christopher.
You really know a way to a man's heart, Christopher. That's all. I am susceptible to flattery. Sometimes people refer to photons as not experiencing time from that photon's vantage point the moment it's emitted from a source and the moment it hits something are simultaneous. Does that mean that the object a photon impacts is deterministic? Let's say, for example, I see a photon from a star 1 million light years away. From my perspective, I just happened to be there when I looked up and the light hit my eye. But from the photon's perspective, it hits the lens of my eye at the exact moment it was emitted. Does that mean that I had to be in that spot at that time because I was predestined to be hit by that photon?
My boy's getting deep.
He just went
deep.
off philosophical. Yeah. Also, he says at the end of that, are you a fan of sativa, marijuana, or... No, I'm joking. I just put that. He didn't say that.
So if we think of photons hitting their destination as a collision, perfectly happy to think of it that way. So if you didn't happen to stand up and stand and look up when the photon hit your eye and you like stepped to the side, the photon would then hit the leaf or the grass or the mountainside or the beach. It'll just be instantaneous with that. So what you're thinking to yourself is that the photon, when it's emitted, sees your eye and then just goes straight into your eye in that instant. But no, 30,000, well, however many thousands of years do pass, and things can happen before the photon hits its destination. So I guess what you're wondering is, does the photon have an awareness, an advanced awareness of where it's going to hit since no time elapses? That's kind of what he's saying there, I think. Is that what you think, Chuck?
Yeah, I think so. I mean, that's one version of predestination. I mean, the other predetermined outcome would be that it was set before the photon left its origin.
Yeah, but I'm just saying, so the three of us are here looking up, and we're on some kind of rotating wheel, right? And so, okay, who's going to get the photon and who's not? And the photon already knows at the moment it was emitted whose eyeball it's going to go into. So that's a way, I have to think about that some more.
Yes, because as far as the photon is concerned, that's the way it has to be, because it actually comes into existence at the time of
that it gets
reaching
absorbed.
its destination.
Correct. And if that's
so it has
case,
to be that way for the photon.
If that's the case, So I have to think about that some more.
Yeah,
that's a good one. All right.
Because it's truly philosophical in nature. But
Well,
what he made me think about,
yeah,
is, what you made me think about in reference to his question, are all the photons that lose out on being seen because they land on some stupid beach.
Okay. Well, I lament. I wrote about this long ago because I felt it. I was on mountaintops getting data for my PhD. And I thought to myself, the photons that come to my telescope and go into my detector and go into my data are serving to have the universe understand itself.
Right.
Because we humans are products of this universe. And what if that photon missed my telescope and just slammed into the side of the mountain? What a wasted trip. I've kept thinking to myself.
That's what I'm saying.
That's sad.
I just traveled 40,000 years to be a part of driftwood?
Driftwood. Or
That's
you're on
terrible.
a beach and you hit someone's buttocks who's sunbathing,
Oh, man. Yeah, exactly. It's like I spent all this time. I passed Neptune. I passed Uranus, only to hit your ass.
Your ass. Past Uranus to hit your ass. No. So I think about the photons. And how about the ones that miss Earth entirely and just keep moving through space? Most of space is empty. And so the universe is filled with photons crisscrossing through the night and the day. And so, I have to think more deeply about the life of a photon.
All right, now that you said the crisscross, now I gotta just pick up on that. So 2 light sources, 2 photons in the emptiness of space.
Yes.
Crisscross.
Yeah.
But they can't hit each other.
No, they can cross each other. They're just waves at that level. So here's the thing. I got into a Twitter fight, mild Twitter fight with Brian Cox, who's kind of my counterpart over in the UK. Not Brian Cox the actor, but Brian Cox the physicist. He's done a lot of BBC TV. In fact, he's on tour. Right. He occasionally tours through the United States. He's got a whole universe show. Okay, this latest one is called Event Horizon, I think. But so I got into a Twitter fight because I said that lightsabers in Star Wars, they could cut things and do damage if they're high enough power, but they can't bounce off each other because the light waves pass through. That's like 2 lasers. They'll just pass through each other. It's not like Ghostbusters, right?
Oh. Don't cross streams.
Don't cross the streams, okay? No, it's whatever. We don't know what happens if that's what happens in Ghostbusters, but it's not a problem with light beams. So here's my point. So I say this, and then Brian Cox comes in. Well, actually, if they're made of gamma rays, 2 gamma rays have a probability of interacting with each other and not passing through each other. They have high enough energy to do this. And then you could simulate what could be sort of a bouncing effect between 2 laser swords. And so I conceded on international Twitter that I got out-geeked in that tweet.
But wouldn't you both be fried? Wouldn't the 2 sword fighters be fried
from the gamma rays? Well, they'll turn into the Hulk. There's other issues. Yeah.
That's true.
That's the least of my concerns about the absence of physics in Star Wars. Just make that clear. Yeah. Awesome. I said it. All right, give me some more.
All right, let's go with Fred Lombardo. Fred Lombardo says, "Good day, Dr. Tyson. Since your numerous references to the idea that dark matter should be called Fred, which is my name, I have thought of myself as dark matter. My question, though, since the Fred particle seems to elude scientists, is it possible that the particle is actually a particle of time itself? This would account for its making up a majority of what seems to construe the universe and explain why a particle, has never been found. Love the show. And please say hi Please say hi to Chuck.
So a particle of time. So that's see, time is a coordinate, just as space is a coordinate. So you'd have to have analog to, is there a particle of space that can move through space the way a particle of time might move through time? And I don't think you can do that. There is the smallest unit of space. Okay, it's called a Planck length. It's very small, and the smallest unit of time would be the time it takes light to cross a Planck length. So, in a sense, space and time are quantized. They're effectively voxels. That's volume pixels, voxels of space and time in the universe. But they're not separately particles in that sense. By the way, I just thought of calling them Fred only because we don't know what it is.
We don't know what it is.
That's all. It's really, you know what it literally is? It's dark gravity. To call it dark matter implies it's matter, and we don't even know that. It's a good bet that it would be. If you're a betting person, that's the odds are in your favor. But so no, I'm not voting for a particle of time. That, by the way, what's that movie? There was a movie where you could collect time and then add it to your life.
Yes, that was with Justin Timberlake.
Yes, it had Justin Timberlake. That's correct.
I forget the young lady's name, but yeah, you could buy time. Time was the commodity.
Time was a commodity.
There was no other. There was nothing else of value in the world except time, and it was the currency for everything.
Right.
And the rich people, had all of it. And the more time you had, the longer you lived.
Well, don't the rich people always have more of everything that everyone else wants? Otherwise, what's the point of being rich?
That's so true. That's it. That's
all I'm saying. So in that one, maybe you can think of those as time particles. I have a time particle and I hand it to you, and then you accrue the time. But it's not clear why that would have anything to do with
dark gravity.
With dark gravity, correct. Or even the acceleration of the universe. So, yeah, there you go.
Okay,
good try.
Well, there you
good
go.
Try. Yeah.
Hey, nothing wrong with trying to find a little self-hype in dark gravity, Fred.
Fred.
Nothing wrong with that, Fred.
And did you know there was a DC superhero briefly introduced? I think it was DC, not Marvel, who's named Fred, and that's his sort of regular name, but his superhero name was Dark Matter. And so
I didn't know.
You didn't know
You're
that.
just making that up
I'm telling you. In my Astronomy Bizarre public talk, I talk about Fred the Dark Matter guy. By the way, I didn't discover that myself. Someone heard me calling dark matter Fred. They say, "Did you know?" And then they showed me a picture.
And they showed you the picture?
It's Fred with all of the properties. It's like, what are your parameters? Your origin story. What are your powers? What are your power limits? And what's your civilian name? This is dark matter.
And his civilian name is Fred. Wow.
Fred.
First of all, that has to be DC.
It's probably DC because they've got a civilian name, right?
Yeah, because Marvel would never make any superhero named Fred. And no offense to you, Fred, but
that's cold. No, take that back. I'm
not.
Chuck.
No, because nobody goes just like, "Help me, Fred."
No, his superhero name is Dark Matter. That's my point.
Oh yeah. Well, still, even still, I mean, think of it. Let's think of it now for a second.
Help me, Fred.
Right, but no, think of this: Bruce Wayne.
Yeah.
Clark Kent.
Yeah.
Peter Parker.
All right.
Fred Farter. Fred what? Fred? No, Fred doesn't work.
All right.
Fred doesn't work. Sorry. Anyway,
we'll send you complaints to the Marvel complaint chat room. Right. Okay.
Yeah, Marvel they have good names. Mm-hmm. Okay, here we go. This is Justin Hansen. Greetings, esteemed Dr. Tyson. My son Tucker, who just turned 11, recently asked me whether reducing the temperature of a radioactive element to absolute zero would give the appearance of the half-life being reduced due to relativistic effects. You are lying. No 11-year-old asked this damn question. Who the hell you think you fooling? Just say you want to know this, Justin. That's all you got to do. Hey, Dr. Tyson.
Pass it off on his kids.
Yeah, I got a question I was thinking about for a long time. You know, it has to do with absolute zero and radioactive elements. Dude, you got to be kidding me. Anyway, 11-year-old Tucker wants to know.
Okay, 11-year-old Tucker is the next superhero nemesis.
Yes.
Superhero, right? What is he building in his basement? All right, we must find that out immediately. Send authorities.
And it ain't good. That's all. I'll tell you this right now. If Tucker wants to know if a radioactive element at absolute zero would give the appearance of the half-life being reduced due to the relativistic effects, you know,
okay,
I say move out now because Tucker gonna blow up your house.
Move out now.
Yeah, move out now. Because Tucker's blowing that joint up.
While you can.
Yeah, there you go.
All right. So that's an excellent question. So as you know, everything slows down as you drop the temperature of things. But when I say everything chemical slows down. Mm-hmm. Chemical things slow down. So the rate at which chemical reactions unfold, it goes to about half the rate for every 10 degrees Celsius. So that's why, for example, it's important that your refrigerator is as cold as you can get it, but not freezing, so that whatever bacteria are growing in your food that would ultimately turn it green and smell nasty, you want to delay that, all right? It's not that food is good until it's nasty. The food is systematically getting nasty until it hits some nose threshold or color threshold that you have held for it.
Right. Unless it's avocado, in which case 5 minutes is all it will last no matter what.
Until it turns brown on the top.
Yeah, right. You take it out 5 minutes later, it's a rotten mess.
No, you put some lemon juice on it. Lime juice is good. It'll work.
All right, I'm going to try that.
What do you mean try that? You didn't know this?
No,
dude,
I didn't know that.
Dude.
Is that for real?
Have you never met a Mexican in your life? It's like, what? You got to get out more.
You know what? Now you're embarrassing me because I'm going to tell you the truth. I don't know any Mexican.
You don't know any Mexicans.
I'm in New York, man. All my friends are Puerto Rican.
Okay, that's true. Yeah.
My friends and my family. I got friends and my family. They're all Puerto Rican or Dominican. If they look like me, they're Dominican.
All right. So for every 10 degrees, so that's why food spoils faster if it's not in the refrigerator. You put it in the refrigerator, it delays it, but it will all still go bad. All right, according to this calculation, for every 10 degrees Celsius, it doubles the rate at which something will happen. Or if cooler, it'll halve the rate. Keep doing this down all the way to absolute zero. You could basically keep food forever. Forever in terms of bacteria that would be growing on it. You have other issues related to the molecular integrity of the food itself. So it can start losing its texture. But that's not because bacteria we're eating at. It's because the molecules themselves are unstable. Here's the point. The moment you go nuclear, then all the things that apply to atoms and molecules no longer apply. Whole other sets of forces dominate in the nuclear regime. And so if you cool things, the nucleus doesn't give a rat's ass. It will still decay at exactly the rate that you had measured for it at any other temperature. If you want to slow down the rate, what you do is you speed up the molecule. Ooh.
Okay.
You speed up the decaying particle. Yeah,
right.
You speed it up. Put it in a particle accelerator. Send it 9/10 the speed of light, 99/100th the speed of light, and it will slow down the decay rate by the exact amount predicted by Einstein's special theory of relativity.
Because anything moving at the speed of light, time itself slows down for that.
Well, at the speed of light, it stops. So you get closer to it.
Stops. That's what I'm saying. The closer you get to the speed of light, the more time.
It's not just the physical watch that, the timepiece that the particle's wearing on its wrist. It's everything about it.
Everything. Right.
Everything, including its very nature, this probabilistic thing that it will decay.
And that's why you say it's time itself that's slowing down, not
anything
the measurement.
Itself.
It's not the measurement itself. It's the thing.
The thing itself. So you're going to look at your clock, and you slow down, your brain slow down, the clock slows down. You don't know anything is slowing down.
You don't know anything has slowed down.
So the particle has no idea that it took quote, longer for it to decay in its own reference frame. But to our reference frame, it takes longer. So if you want to relativistically affect particles that are decaying with half-lives, you just simply accelerate them or put them in a very different gravity field. That'll slow them down too.
Slow them down too. Mm-hmm. Wow. Okay. Hey, Tucker, air quotes, Tucker, let me just say, buddy, you're an amazing kid, Tucker. Okay. Let me you keep at this, Tucker, and whatever you're building in that basement, when you unleash it on the world, just remember, Chuck Nice is your friend.
Chuck said something nice to you.
That's right. Just remember the black man who told you were special. When you were demanding your $1 billion
in ransom.
That's right.
So Chuck, you're agreeing to be his sidekick. You're agreeing to that all the way.
Yeah, okay. Listen, without a doubt.
All right, Chuck, we just finished out that segment. All right, when we come back, more cosmic queries on cosmic collisions when Star Talk returns. Chuck, we're back. Cosmic queries on cosmic collisions of all kinds. Small, large, medium, large, universe, everything. Mm-hmm. And you got the questions from our Patreon members, so keep them coming.
All right, let's do it. This is Don Lane. It sounds like a person from a old-time movie. Anyway.
No, Don Lane would be a game show host.
Oh, you're right. That's right.
That's a game show host name. I'm Don Lane.
That's right. It's Cosmic Collisions with Don Lane. Yeah. All right, here we go. This is, he goes, hello.
Do we watch too much TV, Chuck? Is this a problem?
I don't know. It could be, Don Lane says, hello, Dr. Tyson, Lord Nice. Could moons of outer planets have been born from inner rocky bodies that may have broken off of molten rocky planets in the early formation of the solar system? Could this be proven, or would it change our current understanding of how our solar system was formed? So,
I love it. Okay, let's look at the solar system for the moment. Only once we had sufficient computing power were we able to show. Because we started saying, our solar system is probably representative. And we have some small rocky planets up close and some big gaseous ones far out and some other gaseous ones a little farther out and some comets and asteroids. Why think that we look different, right, as a first pass? When we started collecting data on exoplanets, oh my gosh. Oh, there's like a Jupiter orbiting as close to its host star as Mercury is to our sun, or even closer. And there's all kinds of variation that no one expected. Okay, so all we can say is that there is no standard solar system, star system. That first. Second, when our computer models got good enough, we would create solar systems. You'd say, okay, let's start with 30 planets and see what happens. Oh, they settle out. Some planets get swung into the sun, others get eaten by the bigger planets, and others settle peacefully into their orbits. So it is highly likely that any star system with 8 or 10 planets in it started with 2 or 3 times that many objects. Okay? So yes. Now, if you take that down to a moon system like Jupiter, and I lost count of how many moons it has, 60, I don't remember.
Wow.
There are things it's a ton of moons. There are things you can know. If the moon looks like an Idaho potato,
right,
then it was never big enough for its gravity to shape it into a sphere.
Okay.
Okay. Because
could it? I'm just following up. could it have just been captured by that orbit?
Yeah, no, yes, but wherever it formed, I'm just saying it was never big enough to make a sphere out of itself. So it stayed as a craggy chunk of rock. So it stayed as a, okay,
gotcha.
That's first. Right. Second, if you do see craggy chunks of rock out there in orbit, should we call it a moon? There's a lot of stuff, like, for example, Mars has, how many moons? Do you know how many moons Mars has?
I don't.
It has two moons. Not. It has two moons, Phobos and Deimos, and they are the lamest moons I have. No. They look like Idaho potatoes. One is the size of Manhattan, right? It's like, no, don't make me call these moons. I'm sorry.
Now, why are you moon shaming Mars, man? Yeah, go on. That's cold.
Casting shade on Mars's moons. No, if I gotta be, I know I have some history there with Pluto and stuff, but Pluto was at least big enough to be a sphere, all right? As is its moon, its biggest moon, Charon, was big enough to be a sphere. So there's the Sphere Club, and then there's the Craggy Chunks of Rock Club, and there's a very clear distinction between the two of them. So things you can learn when you see moons around other planets is, well, is it massive enough to have made it into a spherical shape? If it's craggy, it's probably a chunk broken off of some other larger thing that was a sphere, okay? In a collision. So that's another thing you can tell. And also, there's some moons where one half of the moon looks really different from the other half, as though something collided into that half and then took its own shape relative to the side that is 180 degrees away. And a third kind of moon, forgive me, I forgot the name, it's a famous moon, where it looks like some piece of other asteroid collided and got stuck in it. Because if you look at the terrain, it's really, really, really different over in one section compared with another section. And it looks angular, and it's like somebody just mashed it in there. And so there's a lot to learn from the topography of moons, provided they don't have weather systems that erase the record of the collisions you experienced in life. So you take a look at the surface of the moon, it's been hit by some meteors, right? How about Earth? How many craters have you seen on Earth? A few, all right? But we're right next to the moon in the stream of impactors. Were it not for our atmosphere and our weather and other erosive, corrosive forces, we would look just like the moon.
Well, thank God that we have those weather and atmosphere.
Just like the moon. You want to thank God? That's fine, because we're...
Well, thank atmosphere. Okay,
atmosphere.
I'll thank atmosphere and I'll thank weather. Because
no, you can thank God. I don't have a problem with you thanking God.
The moon is ugly. The moon's got an ugly face. That's all I'm saying. The moon is cosmic acne.
Acne, and we have ways of covering up the history of that, the scars of having been slammed. So there's a whole branch of geology and astronomy that has merged as planetary geology, basically. And these are folks who worry about this all the time. Excellent question.
All right.
Yeah.
Excellent question, man.
Keep it going.
All right. This is our old buddy, Alejandro Reynoso.
Okay. Okay.
Hello. I am Alejandro Reynoso. I am coming to you from Monterrey, Mexico.
Is he from Monterrey? Is he?
Yeah, he's from Monterrey.
Oh, cool. So it's all there. You're running the gamut there. Okay, go ahead.
He says
Monterrey with 2 R's, by the way. Correct?
That's correct.
Yeah. The Monterey, California, I think is 1 R. But okay, go on.
And then he says, "Hello."
Stop, Chuck.
Or should I say, "Hola"?
Chuck, that is not what he said.
No, he actually says that.
Okay, go.
He says, if we could see how, if we could see it, how would the collision between 2 black holes look like it? We actually have seen that.
Oh, yeah. Oh, no.
But wait. Then he goes on. All right. How about 3?
Some people just never satisfied.
Yeah, I love it. Oh, that's great.
Okay. You're not likely to get 3 things to hit simultaneously. Just you do the statistics on it, it's just not happening. You can get 2 objects to collide and then collide with a third object, but to have all 3 collide with each other at the same time is statistically sufficiently unlikely to not really want to waste your brain power on that. But we haven't photographed the collision of 2 black holes, but we know exactly what it would look like because we completely know the physics and the geometry and the relativity of what's going on. And all you have to do is Google a YouTube video of the black holes that collided that LIGO observed. So what would be the search on that? Good search for YouTube LIGO colliding black holes. Make sure it's YouTube, and then you'll be a video. And so you'll see the 2, and you'll see their effect on the stars behind them. Okay, that's where the action is, because the space around the black holes are distorted, and it brings things that are in a different place in the background into a new place in the foreground. You have a completely distorted circular images of light around the black holes. It is what you see with those recently released photos of black holes. One in our own galaxy and one in another galaxy called M87. You see a ring of light and then a darkness in the center. So that darkness is basically the shadow of the black hole because no light is coming from it. And what's around it is all the light from distant beyond it that is collected into this ring, which is the effect that black holes have on their environments. So you check it out and you watch it, and then you see this ripple, which is the gravitational wave that got emanated on collision, and that's what we waited 1.3 billion years to detect when we finally turned on the Laser Interferometer Gravitational Wave Observatory. LIGO. Check it out. It's beautiful.
That is amazing.
It is beautiful.
And so now, let's say we turned it on right after Einstein theorized that these gravity waves would happen. Would we have then seen them?
Okay. No, right. So here's the thing. Einstein wrote down an equation for the stimulated emission of radiation in atoms, and it was a small paper in quantum physics, and you had to. That was in 1916 or 17, and then you had to wait until 1957. So that's 40 years later, where someone uses those equations to invent a laser. Okay, the L in LIGO stands for laser. Nobody's detected anything without the laser here. Okay, so Einstein predicts gravitational waves. He presages the discovery of the laser, and then we use lasers to measure the existence of gravitational waves, which means Einstein was a badass. That's all. It's just pure and simple. And he got a Nobel Prize in 1921 for nothing I just said. Okay.
and that's when you know you're the GOAT. Okay.
Greatest of all time.
Yeah,
yes.
when they
Yeah, so what we learned was if you turn on the machine and you discover a colliding black hole a week later, you say, boy, we got lucky. Or maybe these things are happening more frequently than you previously thought. So right now, I forgot the numbers of dozens of colliding black holes that we have data on. So yeah, had we turned it on back when Einstein did this, we would have found them. But where technology and computing wasn't sufficient at the time to have come anywhere near a detection. You would have to wait most of the century. We've got to take a quick break. When we come back, the third and final segment of Cosmic Queries, Cosmic Collisions on Star Talk. We're back, third and final segment, Cosmic Queries, Cosmic Collisions. It's one of my favorite subjects. I could talk about this forever, Chuck. I don't know how many questions we're going to get through. And this is our second installment of Cosmic Collisions. All right?
Yes.
There's probably a third one in there, but we'll give you all a break. Okay? Yeah. So, Chuck, I was surfing the TV, and there you were, your smiley face on Nat Geo in Disney Plus, host of Brain Games.
Brain Games on the road.
We're all proud of you, Chuck.
Well, thanks.
Like,
thanks.
You're not just any random comedian out there. You care about being smart, and we love that. We love that.
Well, thank you. And that is true. Yeah. I appreciate that. Yeah. Mm-hmm. All right, here we go. This is Heps from New Zealand.
All right.
He says, Hello, Dr. Tyson. What's up, funny man? My name, I think I'm the funny man. I'm not sure. The way
I think it's a placeholder for whoever is in your slot.
Yeah, exactly. That's what I'm saying. It's like
That's all right. Go
all
on.
right, here we go. This is Woody. He says, "Hello, Neil, Lord Nice. You know how the melting point of water lowers under pressure. Could two bodies of ice join together in a collision? And what kind of force would it need to make that party trick by whacking the joining ice cubes?" I did try clapping ice a few times while writing this, and no, it did not work.
Yeah, it doesn't
Woody.
work. I'm glad Woody did the experiment in anticipation
This is not a question. He's calling you for confirmation.
confirmation of his experiment. All right, so a fully solid object occupies space that cannot be encroached upon unless something changes about that body. Now, we talked about this before with ice. When you freeze water, it expands, right? So how do I compress an ice cube back to its original volume? You can't unless the ice melts under pressure and becomes water again.
Right.
So you can't shrink the size of ice without ice having to completely change its molecular configuration, okay? From a lattice for the ice down to a fluid, which is then water. So no, you can't take two ice cubes and just merge them into one object. That does not work. But it's true for any solid homogeneous object. By the way, if the object has sort of air bubbles in it or air holes, yeah, you can sort of squeeze things into that for sure. But if it's a uniform solid object, it's not happening.
There you have it, my friend. Woody, you have your confirmation.
Yeah, and you did the experiment. I'm delighted by the experiment.
It was a success, bro.
Oh, by the way, there's some things you can try to squeeze them together, and they won't intersect, but they'll flatten, right? If I take two sort of small cubes of gold, and I try to squeeze them, I won't succeed unless the gold has permission to flatten in all directions. And on doing that, you can flatten two things if you squeeze them, sure. Yeah.
Right. Okay.
But the total volume of what you flattened is the same, just so you know.
Exactly.
Yeah.
Right. Okay. So this is Amanda. Do any of these collisions show any type of light when they happen? I know that there's a lot of light being shown either by stars or explosions that have already happened years ago, but maybe even millennia ago.
Ooh, I love it. Okay, so generally if you have a collision, there's a lot of energy that has to manifest in some way. When you're manifesting energy, often that energy comes out in the form of light of some kind. And light can be any manner, any combination of the electromagnetic spectrum. If any of that comes out as visible light, you will see a flash. There are people who have made a cottage industry of staring at the unilluminated segment of the moon on any given night. Okay, so let's say it's a half moon in the sky. They put their telescope on the half that's not lit, and they carefully look for flashes of light.
And that's an impact?
That's an asteroid impact on the surface of the moon. You're not going to notice it in the lit side because it's too bright. All right? So there's an entire cottage industry of people who do this. All right? And that impact, where does the kinetic energy of the object goes? It goes back into the object. We discussed this in part 1 of Cosmic Collisions, I think. Did we do that, or is that in a explainer? It's all one memory to me now.
Yeah.
The collision of a high-speed impact, where all the energy goes back into the object. Right.
Absolutely.
So if you do that, then it explodes. If that's sufficient energy, like I said, a lot of that energy will goes into infrared, just to heat, and also to visible light. Now, here's something interesting, okay? You know what happens if an airplane goes through the air faster than the speed of sound? You get a what?
You get a boom.
A sonic boom.
Sonic boom.
Okay, so now, what happens if a particle travels through a medium faster than the speed of light?
The entire universe implodes on itself.
So here's the thing.
And we all get sucked into oblivion.
Here's the thing. Light moving through transparent objects other than a vacuum travels slower than the speed of light in a vacuum. Did you know that in diamond, which is like one of the densest transparent substances, light travels at 40% of its speed in a vacuum?
Ooh, so diamonds are the brakes of light.
Yes, they put on brakes.
The brakes for light.
They slow them down. And the slower something moves in the medium, the more it refracts when it bends going through it. The bigger is that angle. So what makes diamonds sparkle is light comes in one place, it multiply internally refracts and pops out another place. So it looks like the diamond is sort of self-luminous, even though you don't think you had anything to do with that.
Right.
So now, when you have a particle that goes through a medium and you accelerate it faster than the speed of light in that medium, it creates a flash of light. And it was discovered by a Russian called Cherenkov, and it's called Cherenkov radiation.
It's a light boom.
A light boom. Yes. Not a sonic boom. It's a light boom.
Not a sonic boom, but a light boom. That's
Correct.
So cool.
Correct.
That is. I just love the diamond little factoid. That's
yeah. So all of this. Yeah. So if you were to put particles through a diamond, you get that effect at only 40% the speed of light. And just a fast fact here: the light actually doesn't slow down.
Okay. We're getting creepy now. This is cool.
Okay. So let's say you're trying to get from one side of a party to the other and it's crowded. Okay.
Right.
So what happens is you bump into someone. You say, "Oh, pardon me, excuse me," and then in the space between you and the next person, you go at the speed of light. But then you hit the next one. "Oh, pardon me, excuse me," and then you go again. Okay. So when the light is interacting with each of the particles in the lattice, it has to get through that particle, and so that takes time. Whereas when it's between the particles in the lattice, it's moving at the speed of light. So you add it all up, there's a net slowdown before the beam comes out the other side.
I got you. Yeah. It's like hurdling.
Okay. Right.
It's like a hurdler.
Hurdler. They're probably going their slowest going over the hurdle.
Jumping over the hurdle. That's right. But then they speed right back up. That's
up.
Very cool. Either that or a diamond is just, just like, slow down, baby.
It's got the music.
Yeah, what's up, Light? Why are you in such a hurry?
By the way, it's true with light going into the Earth's atmosphere, from the atmosphere into water, and water into glass into diamonds.
So any see-through medium or
any see-through medium, correct?
Any see-through medium. That's cool, correct. Man.
You got it.
All right, here we go.
We got one more question. Time for one more question. Make it a good one.
Alain in the Stars. That's the name.
Oh, A-L-A-I-N?
Yes, Alain in the Stars.
That's Alain.
No, A-L-L-A-I-N. Alain.
Oh, Alain. Alain. Okay. Mm-hmm.
Yeah. Hi, Dr. Tyson, Lord Nice, Elaine from Montreal, Canada here. Can a meteor impact create enough energy to spontaneously create particles? Thank you, Elaine.
Oh,
wow.
Yeah. No. It's all the energy of an impact, as ferocious as it is not sufficient to influence atoms. Okay, it's all stuff will break apart. You'll lose your molecules. You might even ionize some atoms, but the nucleus itself is way out of reach of the energetics of a mere meteor impact. So, yeah, the regimes of the universe are very distinct and separate. By the way, that's why we can say with confidence, in the early days when we said, "Oh my gosh, there's such a thing as an atom," and we found electrons, going around a nucleus. Maybe it's just a small version of a solar system. And maybe it's just that all the way down and all the way up. Wouldn't that be cool, like a nested doll? And then we went down there, and we even called the electrons in their path around the nucleus, we call them orbitals.
Orbits, right.
Okay,
right.
Orbitals. All right, we got the word from solar systems. So you go down there and you find out, no, gravity has nothing to do with what's going on. It's got nothing to do with Newton. It has to do with quantum physics, and all the forces are different. And no, they're not analogous at all. And so same when you go very large. When you go very large, certain forces no longer manifest in the same way. So you can't just scale things and claim to get everything the same way. It doesn't work that way.
Wow, look at that. That's really, the universe is a tricky little something.
It's tricky. It would have been too easy if everything just scaled, right?
Yeah.
That'd be just way too easy. But it's not that. It's harder, which means physicists basically have jobs.
It's the trickiness that keeps us employed.
Exactly. So, Chuck, that's all we have time for. And so we got to call it quits there. Always good to have you, man.
Always a pleasure.
This is Star Talk Cosmic Queries, Collisions Edition, our second installment. We'll probably do more, but we'll give you a break from it until you're feeling it. And we start getting requests. I need more collisions. Give them to me. And we'll be there for you on Star Talk. Neil deGrasse Tyson, keep looking up.